Hi everyone, welcome back to Mind and Bats with Amna. Before we go into exact differential equations, let's quickly recall something familiar, separable differential equations. In separable equations, we can rearrange the terms and isolate the variables on opposite sides and then integrate directly. For example, if we have the derivative of y in terms of x as x square is equal multiplied by y, we can isolate the variable y on the left side like this and x on the right side, and then in and then integrate. We are left with a log of y, and over here we have a x cube over a 3 plus any constant, and we can get y explicitly in terms of x by simply using the exponential function. And I know using the laws that this is can be written like this, and therefore we have a y in terms of x as e powers, which is, we can just write this as a constant k, e x cube over a 3, and when we take x is equals to 0, we are left with e power 0, which is 1. Therefore we find the value of the unknown constant being the initial value of the function at x is equals to 0, and therefore I find the final answer of y in terms of nx, and I write it down like this. Okay, so hence, like when we have separable equations, it is very easy, I'll again repeat, to find y explicitly in terms of x, because it's very easy to isolate the variables. Okay, but like this type of but the type of equation we are studying today, exact differential equations, cannot be separated like this. Instead of isolating variables, we use a different idea. The equation comes from a single underlying function fxy. Okay, think of fxy as a three-dimensional surface like this in space, and the solutions to our differential equations are simply level curves. These are the level curves of the surface such that fxy is equals to c, so some kind of at some constant, and it's projected onto the xy plane. So visually, instead of solving directly for y in terms of x, we are finding basically we are finding curves on the surface z is equals to fxy that correspond to constant values of z. These appear as you can say smooth curves in the xy plane. So for instance, the third dimensional surface here is called a utility function, and the level curves or the contours are called the indifference curves associated with each value of z. The higher the value of z, the higher the utility, and the further the indifference curve moves away from the origin. Okay, so now let's take a concrete example and see how we check for exactness and how we recover the function fxy step by step. Now suppose you have the following derivative of y in terms of x. As you can see, it's quite evident that it is not separable. So this is how we're going to solve it. So basically I've just put everything, I've cross multiplied these, and I've put all the variables on the left hand side and put the equation equals to a 0. Okay, so this is basically our first step. Okay, next what I'm going to say, that I'm going to assume, let me zoom in a little bit, that fxy is equals to some constant c, and it describes the above. If you guys want me to speak in Urdu, I can do that as well. But for now, I'm just sticking to English. But I can give the lecture in Urdu as well if majority of my subscribers want the lecture in Urdu. Anyhow, so let's take, I've already given a lecture on how to take the total derivative. So now let's take the total derivative. Okay, so our function is f x y is equals to some constant c. So I'm first going to take the partial derivative of f with respect to x dx plus partial derivative of f with respect to a y dy, and since we have a constant, the derivative of any constant is basically equals to 0. So what was our question? This was our question. Okay, I'll rewrite this again. So in our question, we had, let me scroll up, 2xy plus 3 dx plus x square plus 4y. Okay, so this was our question, 2xy plus 3 dx plus x square plus 4y dy is equals to 0. So you can see that this expression right here, this one, will be the same as this, and the expression on this side right here is the same as this. Okay, so how do we express this? Okay, first of all, we write this equation as a function a function of xy dx plus n as a function of xy dy is equals to 0. And our first step is to check for exactness. So this is how we check for exactness. So I write the function mxy, which is basically multiplied by dx, right? And I say this is equals to a 2xy plus a 3. And then I take the derivative of m, partial derivative of m with respect to a y. And this is basically a 2x. I do the same thing for the function nxy. So nxy is equals to x square plus 4y. And when I take the partial derivative of n with respect to nx, it's going to be a 2x. If both of these answers are the same, then we will say that the condition for exactness is satisfied. Another thing I would like to add here is that mxy is actually the partial derivative of our function f with respect to x. And therefore, this right here is the second derivative of f with respect to y this time. And what was n? Let's write this. N should be the partial derivative of our function that we want to find with respect to y. And therefore, this is simply the double derivative, but with of y with respect to x. Okay, so what we want here is to mention that the condition for exactness is satisfied. So if the partial derivative of m with respect to x is equals to the partial derivative of n with respect to y, then the condition for exactness is satisfied. Okay, so this basically means that there has to exist a third three-dimensional surface. Okay, so this implies that our three-dimensional surface exists. And obviously each solution curve corresponds to a level curve. Maybe I should write this down in case. Each solution curve corresponds to a level curve. It's not a section, it's a contour. F x y is equals to some constant c. Okay, so now that we know that this is an exact, we can move on to finding the solution. So it's easy, it's not that difficult. I'll just divide this page into two sections. Okay, so we know that the partial derivative of f with respect to x was equals to a 2x plus 3, 2xy plus 3. Okay, so if I isolate just the derivative signs, and I take the integral here. Now this y is going to be treated as a constant, so it's treated like a constant, as in a number. So I get a f here because there was a 1 here, and I'll get a 2x square y over x plus some constant. Since y is a constant, so I'll say okay, I'll get some answer with respect to y, a function of y which is a constant. So g of y will be a constant. So therefore I get a f x y is equals to 2 oh sorry, what was I doing? Oops, mistake. X square y plus gy. I'm not gonna edit out my mistake because I want you guys to see that anybody can make mistakes. Okay, so this is the function. Okay, let's suppose I do the same for the partial derivative of y, f with respect to y. This is just for fun. Okay, it was x square plus 4y, x square plus 4y. So again, if I isolate and then I take the integral, x square is going to become x square y plus 4y square over 2, and then we have to add a constant. In this case x is treated like a constant, so I can say there's just going to be some function of our constant x. So f x y is equals to x square y plus 2y square plus something in terms of an x. Now remember, these two have to give you the same answer, right? Because the same function. We have a x square y here and we have a x square y there, and oh my god, what did I do? I forgot the 3 here. There's a 3 here, so basically which is multiplied by x power 0, so it should be plus 1 over a 1. Okay, my bad. There should be, we should have a 3x here. Again, if this was a live class, my students would have pointed out my mistake right there and then. Anyhow, okay, let me fix my mistake over here as well. Okay, plus 3y. Oh, sorry, 3x. Okay, so now these two have to be equals to each other. So how do I make sure that they're equal to each other? What I can see is that what I'm assuming h being a function of x would probably, and it should be, actually equals to 3x. And g being a function of y should be equals to a 2 y square. Only in this scenario will both these equations actually be the same. So if whenever gy is equals to 2y square and whenever hx is equals to a 3x, then we have the same answer from both sides, which is going to be an x square y plus 3x plus what was gy, 2y square. But another thing, like we can do another thing actually. What we can do is that we can, when we find this, so let's just play around a bit. What we can do is that we know that the partial derivative of f with respect to a y is actually equals to this equation right here, right? So I know that this should be equals to an x square plus 4y. So let's take the partial derivative of this unknown function. So let's do it. I'm going to be doing the partial derivative of f with respect to y. It's going to be an x square plus a 0 and then the derivative of this function. And if we equate these, I will get a derivative of y with g with respect to y as being equals to 4y. Okay, this becomes this. And now I can find the function, because this is actually easily separable equation. So I can just find out g from here, because this is basically dg over dy, which is the derivative of g with respect to y, which is equals to 4y. This is separable. I'll just do this, and I'm going to put this here, take the derivative, and I have a g here. I basically g in terms of a y, and then I have a 4y squared over 2, which is equals to a 2y. So therefore I get the same answer. The gy is equals to 2y square. Yeah, so I get the same answer if I same solution this way. Anyhow, so what I can our final solution is basically f x y is equals to a c, and therefore x square y plus 3x plus 2y square is equals to a c. And I made a lot of silly mistakes in this video, but I'm still gonna post it. Anyhow, all right. So that was how to solve an exact differential equation. The main takeaway, I'll give a nice summary, is that you identify the functions m and n, and then you check the exactness condition. And once you've checked the exactness condition, which is that you have to take the derivative of m with respect to, oh, see, there's another mistake here, m with respect to a y, and it should equal the derivative of n with respect to an x. If this condition holds, then we integrate carefully and compare the expressions. And then we write the solution as the level curve f x y is equals to a c. If the concept of the underlying surface and level curves made sense, then exact equations stop feeling mechanical and start feeling intuitive. I'll place the notes and a worked solution in the description for you to download. See you in the next lesson. Bye.